Class
senior.
guarantee better.
Arna.
We don't respond there. WhatsApp now add
Nitish.
చేసాం కదా
Nitish responded. Is this from today? పొద్దున్న
పెట్టాను
పెట్టలేదు.
We are all, as no student responded, please respond and attend the class by 7 o'clock.
Please join by 7 o'clock.
And respond. So respond.
Hello. Yeah, fine. Good morning, students. Yesterday we are discussing about the electromagnetic induction. Electromagnetic induction. Okay. Okay, fine. In this one, we are discussing about the. Yesterday we discussed about the definition of electromagnetic induction and then magnetic flux, and correspondingly we discussed about the Faraday's law. Okay, and finally in the Lenz law we discussed about the induced current, how the induced current will varies. Okay. Okay, fine. And all of you please give your attendance. Hello. Please give attendance. Okay. Okay, fine. Now, today we'll discuss in detail about the Lenz law, okay, and the direction of the induced current. Direction of the induced current. Induced current. Okay, the induced EMF. Okay, from the Faraday's law. Okay, we know that it is induced EMF. E is equal to minus d phi by dt. Minus d phi by dt. Okay, Faraday's law will explains the magnitude of the induced EMF. Magnitude of the induced EMF. Okay, and where phi is the magnetic flux. This induced EMF will causes the whether increase or decrease of the magnetic flux. Suppose if the magnetic flux decreases, if the magnetic flux decreases, then induced EMF will be increases. Suppose phi is less than 0, then induced EMF will be greater than 0. And as phi greater than 0, induced EMF will be less. That is, suppose I'm having a circular coil and I'm having a bar magnet. Okay, not necessarily every time we should consider the bar magnet. We can consider any two conductors. Any two conductors. Then what will happen? Suppose let us consider this is North Pole and this is sorry, this is not South Pole and this is North. Whenever the magnet is moving towards the coil, such that in the coil, inside the coil, I'm having a current which is moving in the clockwise direction, which is moving in the clockwise direction. Then what will happens? It is in the coil we are having a current according to the Ampere's law. Okay, whenever a current is circulating, there will be an magnetic field will be present. Since the current is moving in the clockwise direction, we are having a magnetic field due to the circular coil. We'll have inverse. We'll have inverse like this. We are having. Okay, due to the this one, we are having the magnetic field will be inverse. Okay, we'll join. inverse will be there. So the magnetic field in the circular coil, I'll call it B1. This magnetic field, okay, whenever the we are having the magnet, we are having a magnetic field lines like this. So we are having B2. This B1 will repels the magnet, okay, will repel the magnet such that the magnet will move away. Whenever it is moving away, the magnetic flux, since it is repelling, whenever it is coming, okay, each one is having a magnetic flux individually. Whenever it is moving, what will happens? It is flux will be okay decreases because as it is moving away, the flux will be decreases. Due to that, okay, due to that, what will happens? Induced EMF will be greater. Induced EMF will be greater. Similarly, whenever the magnet is moving away, the circular coil will attract the magnet. So what will happens whenever it is attracting the magnet? Whenever it is attracting the magnet, then the magnetic flux will be more. Okay, more number of field lines will passes. So in that case, we can say that induced EMF will be less. Okay, and always remember that it is induced EMF will opposes or opposite to the direction of the opposes or opposite to the direction of the magnetic flux. Okay, induced EMF, it is opposes the direction of the magnetic flux. Okay, okay, fine. This is what we studied yesterday. Okay, this is what we studied yesterday. Here we are having the different cases. Here we are having the different cases that it is we need to find the induced current, direction of induced current. Firstly, let me explain the induced current. What will be the value of induced current and induced charge? And then I will go to the in different cases how we'll identify the induced current. And students, please focus on this Lenz law and direction of induced current because they are asking theoretical question. Okay, in the entrance exam as well as in the board exam, Okay, okay, fine. Firstly, induced EMF, I got it as E equal to minus d phi by dt. So induced current, I can write it as, okay, according to the Ohm's law, I can write induced current or current is equal to E by R. That is, according to the Ohm's law, we'll write it as V is equal to IR. V is equal to IR. Okay. So here we are having the potential difference between the ends of the conductor, that is induced EMF. Current means induced current. Induced current times the resistance of a coil. So my induced current I is equal to minus 1 by R into d phi by dt. Okay. Okay, fine. So with respect to the induced current, we'll have the induced charge since I is equal to dq by dt. So I can write it as dq by dt is equal to minus 1 by R into d phi by dt. So it is dq, it is minus 1 by R into d phi. dq, it is the small amount of charge induced, and d phi, it is the small amount of magnetic flux. So the induced charge depends only on the change in the magnetic flux and as well as the resistance of the given conductor or resistance of the coil. Resistance of the given conductor or resistance of the coil. Okay, fine. Now here it is the mathematically we can find the magnitude of the induced current and induced charge. Okay. Now here I want to find the, suppose whenever the magnet is moving towards the coil and magnet is moving away from the coil, okay, and circular coil is moving towards the magnet and circular coil is moving away from the magnet, okay, like these different cases are there. In these different cases I want to find the what will be the direction of induced current. Okay, in these different cases I want to find the what will be the direction of the induced current. Okay, okay, fine. Now see here it is, suppose let us consider according to the Lenz law, it says that whenever a conductor is placed near another conductor, okay, near another conductor, suppose I'm having one is circular coil and another one it is solenoid, another one it is solenoid. Since both are conductors, both can produce the magnetic field, both can produce the magnetic field. Okay, so whenever one conductor is approaching towards another conductor, okay, suppose the conductor one repels the another conductor, repels the another conductor. Okay, okay, fine. Now due to the repulsion, okay, due to the repulsion, okay, what will happens, the coil, suppose the second conductor will move away, will move away. Okay, so induced EMF I can write it as according to the Lenz law. Lenz law, in his law he gave the magnitude of the induced EMF as well as he explained the direction, he explained the direction of induced EMF, of induced EMF. Okay. Whereas in the Faraday's law, he gave only the magnitude of induced EMF. He didn't explain about the direction of the induced EMF. Okay, that is one of the drawback in the Faraday's law. And in the Faraday's law, another drawback it is he didn't explain whenever the conductor is placed in a medium, is placed in a medium. Suppose if this circular coil and magnet I kept in a medium having an permeability, he didn't explain how the magnetic field will varies. How the magnetic field will varies. Okay. So all this is explained by the Lenz law. All these are explained by the Lenz law. That is the basic point. Okay. Okay, fine. Now, according to the Lenz law, the induced EMF in a coil is opposes the rate of change of magnetic flux, rate of change of magnetic flux. So I can write it as E is equal to minus d phi by dt. E is equal to minus d phi by dt. Okay, okay, fine. Suppose I'm having the cases, I'm having the cases. Okay, the first one, I'm having a coil. Okay, suppose let us consider, okay, current is moving in an clockwise direction. We can also consider in the anti-clockwise direction also, no issues. Suppose here it is the south pole and this is the north pole, and whenever the magnet is moving towards the coil, and whenever the magnet is moving towards the coil, okay, okay, fine. Now individually see here, inside the coil we'll have a magnetic field. According to the Ampere's law, we'll have a magnetic field. Okay, since current is moving in the clockwise direction, current is moving in the clockwise direction. So here we are having an magnetic field will flow inwards, will flow inwards. Okay, like this magnetic field will flow inwards. Let us consider B1 is the magnetic field produced, okay, in the circular coil, in the circular coil. Now in the magnet, the magnetic field lines. Whenever we are saying the magnetic field lines of a bar magnet, always we will consider the outside the magnet. Okay, outside the magnet only. That is from North Pole to the South Pole. From North Pole to the South Pole. Okay. Inside the magnet means we will have South Pole to North Pole. Inside the magnet means we are having South Pole to North Pole. So here also we will have a magnetic field which is developed inside the magnet. So let us consider B2. Whenever the magnet is approaching, then what will happen? The coil must repel it. The coil must repel means here there should be a South Pole and here should be a North Pole. Right? Okay. Whenever here we are having the South Pole and here we are having the North Pole, okay, that means see here, okay, originally it is current is moving in the clockwise direction. Okay, so in order to oppose it, so the induced current must move in anti-clockwise direction. That is, it must move like this. Okay, for your understanding, I keeping arrows. Generally, we will keep like this one. Okay, here it is. The induced current will move in the anti-clockwise direction. Okay, that is the first case. So that means before finding the direction of induced current, before finding the value of induced direction of the induced current, okay, here we are seeing that it is whether the first conductor or any other conductor, okay, one conductor is repelling the another conductor or attracting the another conductor, repelling the another conductor or attracting the other conductor, attracting the other conductor. Depends on that, here we will have the poles. Okay, suppose this is the magnet is moving. Now I will consider that if the magnet is moving away, if the magnet is moving away from the coil, moving away from the coil, that is, suppose second one, it is I am having a coil same in the clockwise direction. Okay, current is I with south pole and this one it is north. Okay, now you can see that here it is. Okay, now you can see that here it is magnet is moving away from the coil like this. Magnet is moving away from the coil. When magnet is moving away from the coil, then what will happen? Here it is. Here it is. We are having an inside the each conductor, that is inside the coil and magnet, we are having a magnetic field lines. That is, here we are having an magnetic field lines will be inverse, will be inverse, and inside the that is in the magnet will have the magnetic field lines will flow from the north pole to the south pole, north pole to the south pole. Okay, here B2 is the magnetic field due to the bar magnet or simply magnet, and B1 is the magnetic field due to the circular coil, due to the circular coil. Okay. Whenever the magnet is moving away, the coil must attract the magnet. Okay, the coil will attract the magnet. Okay, say for example, okay, even you can see in our real life, okay, whenever any physics teacher, okay, any physics teacher, what they will say it is, sir, physics is very hard or physics is typical means they will repel it or they will contradict the statement. They will contradict the statement. Okay, okay, na? Okay. So whenever they are contradicting the statement, then how many number of field lines is coming from the student. Okay, some people will argue and some people will be calm. Those who are arguing, after some time it will be calm only. Okay, suppose if anyone is saying that it is physics is easy, sir. Okay, say for example our Ginny, like Ginny, he will say physics is easy, sir. Okay, then what the teacher will do, it is okay, let me see how much it is easy, how much it is easy. Okay, then there will be interaction between the teacher and student. Okay, whenever I am contradicting, the interaction between the student and teacher, it is less. Whereas in the, whenever I say the easy, that is agree statement. Okay, in that agree statement, there will be an interaction between the student and the teacher. So due to this, we can say that, okay, whenever a coil attracts the magnet, will have more magnetic flux. Will have more magnetic flux. In this case, I can say flux will be greater than zero. Flux will be greater than zero. In this case, what will happen? As it is moving away, flux will be decreases. Flux will be decreases. Okay, flux is nothing but number of magnetic field lines, okay, which are passing perpendicular or normal to the surface area, can be called as magnetic flux, can be called as magnetic flux. Number of magnetic lines of force or magnetic field lines that are passing perpendicular to the area of the coil, area of the conductor, can be called as magnetic flux. So, in order to attract, coil must attract the magnet. In order to attract, here must have, we should have north pole, and here we should have south pole. We should have the south pole. So, here we are having the, here we are having the current. Okay, okay. Now we are having that it is north pole. So, the induced poles are induced current. Induced current. Okay, here it is from north pole to south pole. So there will be an okay, magnetic field will be produced from north pole to the south pole. So induced magnetic field or induced current, it will move in the anti-clockwise direction. In the anti-clockwise direction. Okay, like this. Sorry. Induced current will move in the clockwise direction. Okay, induced current will move in the clockwise direction. Here, whenever the coil magnet is moving away, then what will happen? The coil will attract the magnet. So near the end of the magnet, we will have the north pole because of due to attraction, and the other side will be south pole. Since it is repulsion, near to the end of the magnet, we will have the same pole should have. Same pole should have. Okay, here it is south pole and here it is north pole. Okay, fine. Whenever it is attracting, okay, here I am having the north pole and here I am having the south pole. Okay, fine. Now here it is induced current. Current is moving. Okay, current is moving in the from north pole to south pole. That is in the anti-clockwise direction. So induced current will move in the clockwise direction. Okay, I induced, it is moving in the clockwise direction. Okay, yeah, fine. How the coil changes the means? See, suppose here it is. Whenever the, suppose or else this one, whenever the magnet is moving towards the coil, what will happens? What will happens? See, in this case, whenever the magnet is moving towards the coil, then what will happens? Here we are having at this end, we are having the south pole. We are having the south pole. So this coil must repel the magnet. Must repel the magnet. Okay. Okay, fine. So due to the repulsion, if I have south pole here, okay, that means at this end magnet is coming. So at to this end, so both should have the like poles. Both should have the like poles. Then only coil will repulse the magnet. Then only the coil will repulse the magnet. Okay, that is number one. And number two, you can see, suppose you can see what happens. It is sometime before, okay, sometime before, whenever the SAR asked, okay, whenever the SAR asked, after, I think after first year exams, I think, whenever SAR asked to Ginny, how your teachers will teach, or what will be the teaching style of your teachers. That time he explained something, sir. That means, how you know this? That means he got induced by the teachers. He got induced by the teachers. That is, without supply of any energy, without supply of any energy, okay, or without supply of any external work, okay, the coil or conductor will induces the charge from the magnet, from the magnet. Okay, that is, since it is a conductor, it will absorb the charges. It will absorb the charges. Oh, that one. And that is some of, suppose if I am absorbing, if the coil is absorbing, suppose let us consider two charges, 2 coulomb. Here it will be 2 coulomb, it is less. In the same manner, magnet will also get induced. Magnet will also get induced. Okay, magnet will also get induced. So here it is that you can say coil is stationary. It will have a magnetic field B1, but magnet is moving here in my case. So as the magnet moves, whatever the conductor is moving, that conductor will have an magnetic field will be varies with respect to time. That we are called as time varying magnetic field. Time varying magnetic field. Okay, time varying magnetic field. Okay, fine. Now that is, here it is, the coil must attract. The coil must attract means here should have north pole and here should have south pole. Then only the coil will attract the magnet. Okay, right, Umar? Okay, na? Here the coil must repel it. So that's why the side in which the magnet is coming, that side will should have the like poles. You should have the like poles. Okay, fine. Here it is attract. So the induced current will have in the clock direction. Will have in the clockwise direction. Okay. Okay, fine. That is second one. Now see here, I kept the south pole near to the coil. Okay. Now what I will do it is, I'll keep north pole near to the coil. Same, moving towards the coil and away from the coil. Moving towards the coil and away from the coil. Okay. Suppose third case, it is, I am having a coil and I am having a magnet. I am having a magnet. Here it is north pole and this is the south pole. And this is the south pole. Okay. Okay, fine. Now here it is that initially the magnet is moving away from the coil. Okay. And this coil is having a current which is moving in the clockwise direction. I can also consider anti-clockwise direction also. That is not an issue. Okay. That is not an issue. Okay. Whenever the coil is, whenever we are having a coil such that current is moving in the clockwise direction, that means magnetic field will flow inwards. Magnetic field will flow inwards. Okay. Just like before. Okay. And here also we are having the magnetic field lines from the north pole to the south pole. From north pole to the south pole. Okay. North pole to the south pole, it is having the magnetic field lines. Okay, fine. Whenever it is moving away from the coil, then this coil must repel the magnet or must repel the motion of the magnet. Okay, sorry, not here. Whenever the magnet is moving towards the coil, then the coil must repel the magnet or must repel the motion of the magnet. In order to get the repulsion, okay, the end at which magnet is coming, that end should have the like pole. Should have the like pole. So this is the north pole and this is the south pole. Okay. So that is this is the generation or similarity of the magnet with respect to the coil. Okay. Now induced direction means it must be opposite. It must be opposite to the original direction. Here current is moving from here current is moving. Okay. This is the north pole and this is the south pole. This is the north pole and this is the south pole. Current is moving in the clockwise direction. Due to that, the poles are induced. Due to that, we are having the poles are induced. That is, here it is north pole and this is the south pole. That is, induced current will move in an anti-clockwise direction. Anti-clockwise direction. Similarly, I am having the magnet is moving away from the coil. Away from the coil. Okay, like this. Such that here I am having the north pole and this is the south pole. This is the south pole. Okay. Okay, fine. These are the four cases when magnet is moving towards the coil or away from the coil. Now, next another four cases it is that I will consider magnet as stationary. I will consider magnet as stationary and I am considering that it is coil is moving towards the magnet and away from the magnet. Now, what I am doing it is coil is moving towards the magnet and away from the magnet. Away from the magnet. In that case, what will be the direction of the current? In that case, what will be the direction of the current? Okay. Say for example, it is I think fifth case. It is we are having the north pole and we are having the south pole. And here I am having a coil. That is, coil is approaching towards the magnet. Coil is approaching towards the magnet. Okay, such that suppose let us consider current I is flowing in the coil. Okay, and here we are having a magnetic field lines. Okay, magnetic field lines. Okay, in this case, generally what will happens since in the coil it is moving such that it is moving, let us consider moving with a velocity v. Moving with a velocity v. Okay. And afterwards, okay, we'll consider that we are considering coil is moving with a uniform velocity or in a straight line. Okay. Afterwards, I will consider and somewhat high level, that is whenever the coil moves abruptly or quickly, or whenever the coil is moving slowly, that is 0.001 meter per second, what will happen? or whenever the coil is moving with a velocity 120 meter per second or 200 meter per second, that we can call as a quick approach. Okay, that case. Okay, fine. So suppose here it is the stationary. Okay, so whenever the coil is moving, the magnet will repel the coil. The magnet will repels the coil. So whenever the magnet repels the coil, that means that here we should have like poles south and then north, right? South and then north must be present. Okay. So this is the due to the repulsion. So for this one, we should take the opposite direction. Okay. Since it is the due to the repulsion, we got the poles. We got the poles. Okay. So that means here it should be North Pole. So here must have N dash and this is S dash. Right? Generally, the current will flows from the North Pole to the South Pole. Or particles will move from the North Pole to the South Pole. North Pole to the South Pole. So here we'll have the induced current, the direction of the induced current, it must be this one. Now, see here it is, we are having the particles are moving from North Pole to the South Pole, okay? Approximately, I can say that it is moving in the clockwise direction, right? Hello? North Pole to the South Pole, okay? Induced current, it will move in the anti-clockwise direction. I induced, it will move in the anti-clockwise direction. Okay. Now, see here, it is in the magnet, current is moving in the approximately clockwise direction. Clockwise direction. And the induced current in the coil is moving in the anti-clockwise direction. Okay. Now, just remember one thing. Just remember one thing. In the moving charges, what we studied it is if we are having two parallel straight wires. If we are having the two parallel straight wires, having the currents I1 and I2, if both are having in the same direction, if both are having in the same direction, we thought or we discussed it as the wires will get attract each other. Wires will get attract each other. That means this separation distance will be decreased. The separation distance will be decreases. Okay. Suppose we are having the same two parallel straight wires, having the currents I1 and I2 are opposite in nature. That is, one is moving vertically upwards and another one it is moving vertically downwards. Then what will happen? It is these two wires will get attract. Will okay. Here it is attract nature. Here it is repelling nature. Okay. D will be decreases whenever it is attract and whenever it is repel, it is D will be increases. This is the D. D will be increases. Okay, fine. So that is whenever the currents are in opposite in direction, we will have the repel nature. So here also, what will happens? The magnet is repelling the coil. Okay. Whenever the magnet is repelling the coil, the current flow in the magnet and current flow in the coil must be opposite in direction. Must be opposite in direction. For example, it is attract. It must be same in direction. It must be in the same in direction. Then we can say that okay, both magnet and coil will get attract. Suppose for the same thing, you can see here, I'm having a magnet with North Pole and South Pole. Okay, and I'm having a coil which is moving away from the magnet. Okay, I'm having a current I. Okay, which is moving away, which is moving away. Okay, okay, fine. Now see here, it is current is moving the clockwise direction. Approximately it is in the clockwise direction. Okay, so now I want to find induced current. Now I want to find induced current, under which case, magnet will attract the coil. That means whenever the current is moving in the same direction, okay, like this, okay, then we can say that, okay, here it is, magnet will attract the magnet. Okay, magnet will attract. So that means here we should have the induced current. It must also have in the clockwise direction. Then only it will get attracted. Okay, due to the repulsion, here it is opposite in direction. That's why you got anti-clockwise. Whenever in the case of attracting, then what will happens? Whatever the direction, that is, here also should have north pole, and here also should have south. Okay, and the direction it is from like this. Okay, induced current it is same, but whenever it is repelling, it is opposite to the direction of the current produced. See here, current it is moving the clockwise, but induced current it is anti-clockwise. You may ask me why. Here it is, sir, why we are taking in opposite direction? Induced current, why we are taking in opposite direction? Why not here? Anyone got? See, in this case it is repulsion. Okay, due to the repulsion, okay, we are moving, or we are throwing a conductor to the far away, okay, due to that we are having the, okay, induced current which is opposite to the direction of the current passing through the coil, but whereas here it is attracting. Okay, attracting, whatever the, in which direction we are having the magnet, okay, in the same direction we'll have the induced current, okay. On this topic, okay, on this one, okay, many theoretical questions are there, many theoretical and very good conceptual based questions are there, very good conceptual based questions. Sometimes in the JE mains and even in the JE advanced also, single correct and multi correct, they asked on this lens law, okay, the direction of induced current. Okay, okay, suppose I got the direction of the induced current. I got the direction of induced current. Now I want to find what will be the direction of induced. Okay, na? Is it fine? So, since according to the Ohm's law, I can say that induced EMF equal to induced current times resistance of the coil. Resistance of a coil. So, here we can say that the direction of induced EMF is along the direction of the induced current. Is along the direction of the induced current. That is, I think in the electrostatics and current electricity, we discussed the Ohm's law. With respect to Ohm's law, we discussed that it is, here see, we discussed the direction of the current, from negative terminal to positive terminal. Okay, how we decided that means, can see, particles or electrons will flow from, okay, high potential to low potential, such that the direction of the potential difference, in which direction it is moving, okay, that is positive to the negative terminal, that is moving in an conductor, but inside the battery it will move from negative terminal to positive terminal, or cathode to anode. But inside the conductor, you can see, we'll consider the conventional direction. We'll consider the conventional direction. Okay. Okay, fine. Like this, we are having the different cases. Okay. Different things. Okay. Okay, fine. Once concentrate today about the Lenz law and the direction of induced current and induced EMF. And induced EMF. Okay. Okay, fine. Write down one question. All of you, please open the notebook and write down one question. And write down one question. That is, a current I is equal to, a current I is equal to 2.5 times 1 plus 2t multiplied by 10 cubed ampere. I is equal to 2.5 into 1 plus 2t into 10 cubed ampere. Increases at a steady rate. Increases at a steady, STADY, steady rate. Increases at a steady rate. Okay. Increases at a steady rate in a long straight wire. In a long straight wire.